we have to know what a capacitor is. So a capacitor is there's an electronic device that is capable of storing charges. So that is a capacitor. And it has a symbol. So let me give the definition here. So a capacitor is an electronic device capable of is an electronic device which is capable of storing electrical charges. Okay, so within this device that we are talking about, charges are stored temporarily. It's not for permanent storage, but just a temporal storage of the charges. So when you look at some of the appliances that we use in our various homes, when you switch off your socket that is connected to that power appliance, you realize that the power indicator of the gadget still stay on for some time because before it now goes out. Okay, so it as a result of the charges that have been stored in the capacitor that are within the system that still make your appliance stay for some time before the indicator light stop. So it has this symbol in the circuit. Okay, so when you look at the electrical circuit, you can have the symbol of a capacitor to be like this. So this is a symbol. Okay, so these are all called the power plates. So is there like the terminals or the battery that you see, or a cell? But the only difference between a capacitor and a cell is that for the cell, you have polarities. You have the positive and the negative terminals, which the positive one is always longer than the negative terminal. But for capacitors, the plates are parallel and they are having the same size. So capacitors, they don't have polarities. You can have charges that are situated at one plate. Maybe you can have negative charges at one plate and then positive charges also at the other plate. But that doesn't mean that you have current flowing from negative to a positive terminal. Okay, so this is the symbol. So now that we know what a capacitor is, we can also define the capacitance. So capacitance of a capacitor. Now, the capacitance of a capacitor is the effective capacitance or the effectiveness of the capacitor within the circuit. So let's say if you have more than one capacitor within a circuit, now what is the total capacity that that circuit can store electrical energy? Okay, so if you have the capacitor being connected in the series connections or in the parallel connection, so what would be the total storage in that circuit? So you have to find the effective capacitance depending on the arrangement of the capacitors. So you can have the individual capacitors being summed together, or you can have the individual capacitors being taken the inverse and then summed together. That will be dependent on how they are arranged within that circuit. So we always say that is the arrangement of conductors that are used to store a charge or electrical energy. So the capacitance of a capacitor is the arrangement of capacitors in an electrical circuit used to store charges. Okay, and it is defined mathematically as this. Mathematically, the capacitance is given as so let's say C is equals to the number of charges, that is a charge capital Q divided by the PD across the circuit, that's the voltage. So V. So we can say C is equals to charge on V. And this will give us our equivalent capacitance. So where V is the potential, difference between the conductors. Okay, so the unit for the capacitance, the SI unit for the capacitance is given as coulomb per volt. In other words, you can say it's farad, F-A-R-A-D, which is the same thing as capital F. Okay, so you can use capital F or use the coulomb per volt, because when you look at the formula that we have, the unit for charge is coulomb and the unit for voltage is volt. So it can be coulomb per volt, which is the same thing as farad. So you can say that 1 farad is equals to 1 coulomb per volt, or the amount of charges that are stored within the capacitor per unit, the potential difference. Okay, are we there? So as I mentioned the symbol earlier, you can have another one. You can also see something like this in the, I come back here. So let me add this too. So you can also see the symbol of a capacitor to be like this. So this and something like this. So this can also be a symbol for the capacitor. Okay, but mostly because of the sizes, they are normally recorded in terms of pico scale. That is 10 to the power minus 12. They are always small. So when you say picofarad or microfarad. So you are reducing to a prefix. Okay. So we don't actually have a specific types of a capacitor. The types comes as a result of the shape. And at times too, you also use the dielectric substance to classify them. So depending on the dielectric substance that is used to produce that capacitor, so you can call it in that time. Maybe if you use a paraffin wax as your dielectric substance, it can be a paraffin capacitor, you can call it that way. Or you can also use the shape, whether it is spherical, it is a parallel plate capacitor, or it is a cylindrical capacitor. You can always coin the name from either the shape or the dielectric substance. So when I mention a dielectric substance, these are just an insulators or an insulator that is placed in between the parallel plates of the capacitor, because we presume that the charge does not transfer or move continuously within the capacitor. Because if the charges are flowing from one plate to another, there is no way that there's going to be a charge stored. So we always presume that there is a dielectric or let me come back to the symbol. So like this plate, so there can be positive charges stored on this plate, and negative charges will also stored on this place. Now the gap between them is what we presume that there is a dielectric substance, and this dielectric substance is what I'm saying that they are insulators. So there are insulators, and we know what insulator does. Insulators are materials that do not allow electric current to flow through them. So once they can move through the dielectric substance, so we have the tendency or the potential of storing charges. If it were to be like the normal cell that you have the positive and the negative terminal, then and there is nothing in between, then you can have these charges being exchanged to agree because of attraction. But in the capacitor, it's not like that. So we can also calculate the capacitance based on the dielectric substance that is being used. Okay. So if you have the dielectric substance to be a space, which we are always calling the emissivity of the free space, you can write your capacitance like this. So we can also say the capacitance of a substance is equals to the epsilon naught. We have the area over D, where the epsilon naught is the permittivity free space or of space. Then we have A as cross-sectional area. Sectional area. And then we have D as the distance. That's the separation between the plates. Distance between the two parallel plates. Okay, so you can have this, and this would be our D. Now, depending on, so you can have our plate be like this. So this would be the plate that the charges are stored. So you can also have another plate in this manner. Okay. So this is where we find the area. So the area that the charges are occupying within the plate. Okay. So here we can have our negative charges, and then we can have our positive charges being accumulating in one of the plates. So we use this to determine the capacitance. And still in between the plates, that is what we have our dielectric substance being placed inside. Okay, so let's see if we have capacitors being combined. These are just for a simple capacitor within a circuit. But let's say if you now have more than one capacitor in the circuit, so we are looking at combination of capacitors. So let's say we have these capacitors that are connected to a cell. So let's say we have about 3 capacitors. Make one test it. Let's say we have 3 capacitors as shown, and this is connected to a PD. So let's say this is positive and this is negative. Okay, so here is our voltage. Now let's give this one as C1, C2, and then C3. C3 as shown. So now we see that the capacitors are connected in series. So what would be the equivalent capacitance when you have an arrangement like this format? So we have to use our formula. We're saying that capacitor is equals to charge over V. So when the capacitors are connected in a series like this, it means that the potential energy is going to be same for all the capacitors. The potential energy that is going through the capacitors is going to be the same. So if you pick the individual one, so in terms of C1, C1 will be equals to charges stored in C1. So let's say the charges that are stored in C1 is named as Q1 divided by the potential difference. When you also pick capacitor 2, it will give us charges stored there as 2 divided by V. And the same way, when you pick 3, it will give us charges 3 divided by V. Okay, so if we want to get the total charges and then the total capacitors. So we can say that the total charge, which is Q, will be equals to the sum of the charges that are stored in the individual capacitors. So plus this. So this will give us our total charges that are going to. So we can make the charges from this equation the subject. Charge 1, charge 2, and charge 3, the subject from these 3 equations. So let's say this is equation number 4. So by doing so, you have charge 1 to be equals to C1, and we have V. So let's do that. So we are going to have Q1 to be equals to C1V, and then Q2 will also be equals to C2V, and then Q3 be equals to C3 and then V. Now we are going to substitute this into the expression 3, where we have the total charge to be the sum of the individual charges. So our Q, which is the total charge, will now be equals to, instead of charge 1, will be C1V plus C2V plus C3 and then V. Okay, so you see V is common throughout. We can factorize V out. So charge will be equals to V, open bracket, we have C1 plus C2 plus C3. Okay, so let's come back here and see how we define our total capacitance. So we define our total capacitance as C on Q. So we can make V the subject here too. So when we make V the subject here, that will give us Q on C. Okay, so we are saying that but C is equals to Q on V, which implies that we'll have our V to be equals to Q on C. So we have Q to be equals to Q on C. Q on C. That is Q on C. Yeah, in bracket C1 plus C2 plus C3. Okay, so we need to make C the subject. So this will cancel this.
Your screen disappeared. I don't know whether it's my side.
Well, please check and confirm for me. Please, is it showing?
Yeah,
Yes, it's showing.
it's come now. It's come now. Thank you.
And it means it's a network. I think let me check something, because what we are coming to arrive at will be the opposite. So I made it here. Yeah, so here would be V1. The V is not common here. I thought I'm proving the parallel one. So V1, V2. Okay, so the charges that are going to be common, because the charge that will flow through V.
Please, the screen is no longer showing.
It's your network. It's your network.
Really?
It's your network.
It's showing. It's showing.
So we have
Check
this
your
one, V would rather be this. So let's make that substitution here. Q is going to be common. Q1 will be equals to Q2 is equals to Q3. I was rather proving the one. So this is the same thing as this, which is the same thing as that. But our V, that will be V1, and this one will be V2. This will be V3. Okay, so charge is going to be same throughout here. So we now have Q3. Okay, so the same scenario. Now we have to find our total V. So V will be equals to the sum of the individual V. So this V will be the sum of V1 plus V2 plus V3. So rather make our V1, V2, V3 the subject and substitute into in this equation 4, substitute into equation number 5. So from here, the next slide, we'll have V1 should be equals to this overcharge. So here will be V1, to be equal to this over charge, then V2 will also be equals to C2 on charge. C2 on charge, and then finally V3 will be equals to C3 on charge. Okay, so we sum all the V's together. So we have our total V to now be equals to this. This was for the parallel connections. So we have C1 over Q plus C2 on Q plus C3 on Q. So, but we also define our total capacitance as C over Q. So we said from here that C is equals to Q on V. So this implies that our V will be equals to Q on C. Okay, or it's already here. So we already have it here. So we now substitute Q on C into this equation 6. So when we do that, we'll have Q on C. So let me write out this before. Okay, so now we have Q on C as V. So Q divided by C will now be equals to, we have C1 over Q, C2 on Q, and then C3 on Q. Okay, so we factorize the Q out. That will be 1 over Q, 1 over Q. I show my substitution is all, because it's supposed to be the inverse here. It's Q over C1. We are making a mistake here. I've not corrected. So here is supposed to change. I already equate to the V, but I didn't change. I was told. So this one should be Q on C1. Because of the previous error, I have not changed this. So this one will be Q on C1, Q on C2, and then Q on C3. Okay. So Q on C1, Q on C3, we substitute it here. We're going to have Q factorized out as constant. Then we have 1 over C1 plus 1 over C2 plus 1 over C3. So we can cancel the Q out if we divide 2 by Q. So divide 2 by Q will cancel out. So we'll be left with 1 over C, 1 on C to be equals to 1 over C1 plus 1 over C2 plus 1 on C3. So it means that our total capacitance or our equivalent capacitance CT will now be equals to 1 over CT equals to 1 over C1 plus 1 over C2 plus 1 over C3. So which means that if you have more than one capacitor in a circuit and these capacitors are arranged in series, then the total or the equivalent capacitance will be the sum of the inverse of the individual capacitors. Okay, so this is opposite to resistors. So resistors in series, you will sum them together to get the total resistance. But for capacitors, we go with resistors in parallel. So it alternates. If we even forget about how to sum it, just think about how resistors are at. Then when you understand resistors in series will be the sum of the individual, then you change it, you swap it with the capacitor. So this one is for parallel series capacitors. So capacitors connected in series in an circuit or in an electric circuit. Okay. So that is how we solve it. Now, when you take the parallel connections, it also take the form of the resistors that are connected in parallel. So let's say we have, we can generalize this. If we have a lot of capacitors, so we can always write the total capacitance to be equals to the sum of the capacitors. So taken from I is equals to 1 to n, where n is the number of capacitors. So we can always say 1 on Ci or Cn. So that is the condensed form. The condensed form of writing the capacitors. Okay, so the same way, when you also have them in a parallel connection, so what we look at is series. So parallel connections. So if capacitors are also connected in parallel, you have them arranged this way. So let's also say we have 3 capacitors that are connected in parallel like this, and this is taken to potential difference like this. So V. So here we also have our C1. So C1 here, C2, and then C3. So the PD across the parallel connection here is constant. So here PD is constant. For all the capacitors. Okay, but the charges stores are varied. The charges stores.
Hello, sir.
Yes.
Please, sir, because of network, I did not get the condensed form of the formula that you've written there.
Okay, I'll go back.
Please, can you go right?
Okay. I'll do that. So we're saying about the charges store in each are different. So here the condensed form is C. This is the expand form when you expand it, but the condensed form is this part, this one. Okay, so we are saying that the charges that are varying, but the potential difference across the capacitors connected in parallel is constant. So we also use the same format. So we know that the capacitance is equals to the charge over the voltage. So since the charges are varying, so your total charge stored will be equals to charges stored in capacitor 1 plus the charges stored in capacitor 2 plus the charges stored in capacitor 3. Now, using this formula, so C1 will store Q1 and then V is constant. C2 will also store Q2 and then V. Then finally, C3 will store Q3 and then V. So we need to make Q1, Q2, and Q3 the subject and then put it here. So we do that just by multiply both sides by the voltage. So it means that our total charge, which is Q, will be equals to Q1 will be C1 V plus C2 V plus C3 and then V. Since the voltage is constant, we can just pick the voltage out. So you have V open bracket C1 plus C2 plus C3. Now we substitute from here, implies that our K will be equals to CV. So in place of the Q here, we substitute CV there. So which means that our CV will be equals to V open bracket C1 plus C2 plus C3. So we can divide through by V, and which means that our total capacitance will be equals to C1 plus C2 plus C3. So this will be the equivalent capacitance for capacitors arranged in parallel. So in the condensed form, you can have a CT to be equals to the sum of I is equals to 1 to the number of capacitors that are present. Then you have Cn or Ci. So that would be the condensed form of writing this. Okay, can we move on?
Yes, sir.
Okay. So one thing you should also understand is that the charges that are stored in the capacitor is seen as the potential energy. Okay. Because they store the potential energy at a height. The charges are stored within the plate, so it is seen that the energy that is being stored is sort of potential because the charges are not moving. So it will be in the form of potential energy. So let's look at the applications where we can have these capacitors being applied and their functions in the circuit. So what are some of the applications that we know, or why do we think there is a need for us to always have capacitors added to our electrical appliances that we are having? All our gadgets that we are using in our homes, our phones, are having capacitors in them. So what are the functions? These capacitors that are there, what are their functions inside the gadgets that we are using? Yes, any other person? Anyone?
Yes, sir.
Okay.
Sir,
So
they are using flash cameras.
they are using,
Flash camera.
okay, so that's one of the gadgets that you can find the capacitor, but what is actually the use of it in the camera? What function does it give?
Sir, to store and release charges.
To store charges, okay. And what again?
Is
Power
that some are used
supply.
for decoupling?
Come again?
Power
Some are used
supply
for
feature.
decoupling. They are okay, sorry.
So some are used for decoupling.
Yeah, decoupling.
Okay.
That is to remove a noise or an
Yeah,
interference in electric circuit.
that to smoothen the current. It can also be used as okay. Yeah, any other person?
Power supply featuring.
Okay. So these are just some few applications or uses that you've mentioned. So when you are dealing with uh, yes,
I came across they say one for teaming. It is for teaming. I don't know the meaning of the
for
word teaming.
tuning.
Timing.
Teaming.
Timing.
Yes. Is it timing or timing? Okay, timing. Okay.
Okay. So these are some of the applications or the uses within the electrical circuit. Especially when you are also dealing with an AC. See, AC current move continuously. And so the purpose of the capacitor is to smoothen the pulses that it will be having. Because it's an AC, you have off on. So you see that your light will come on for some time, it goes off in that order because of the pulses that it will generate. So when you put the capacitor inside there, it will smoothen the current. So that's why somebody is talking about the to remove noises or to smoothen something. Okay, so that is the purpose. So we saw that the capacitor can also be calculated. So when you look at the formulas that we wrote, the two formulas that we wrote, see the capacitor is, or the capacitance is directly proportional to the area and inversely proportional to the distance between the parallel plates. So it can come as an objective question. So when you look at the capacitance in a circuit, does it depend directly on the area, inversely on the area, or the diameter and the distance, directly proportional to the distance or inversely proportional to the distance? And you have to also know why the capacitance increases with what? Increasing area, because the capacitance is directly proportional to the area. So it means that if more charges are able to accumulate within a surface, then you expect the capacitance to be high. Okay, because the larger the area, the more the charges. And once there are more charges being stored, then you have a higher capacitance. And when you also look at the distance between the parallel plates, so the narrower the distance between the plates, then the more the charges are stored. But if the distance is wide, then you have a less charges also being stored. So take note of how you can calculate for capacitance of it, of a material. Okay, so let's talk about the dielectric substance that are inside the capacitors. I mentioned that there are insulators or material that do not allow electricity to pass through them. So dielectric substance. Okay, so when you pick parallel plate capacitor, for instance, so you have one of the plates, then you have the other one. So this is our D. So what is filled within the plates is our dielectric substance. So let's say the lower part of this stored negative charges, and the upper part of this plate stored positive charges. So that's why we are saying that for C is proportional to A, that the capacitance is proportional to A. Then this same C is also inversely proportional to the inverse of the diameter. We also have this to be like that. Now, when you put the two together, so you have our C to be equals to, we introduce the constant, that will be K. They have epsilon. Okay, let me put epsilon because we are not dealing with the free space. So epsilon. Then we have A over D. So when you look at this equation, so let's say our K is 1, the constant is 1. Once constant is 1, so we are saying that C is equals to epsilon A on D. So this time around, this epsilon is now the permittivity of the material. Permittivity of the material. So this epsilon now here is corresponds to the dielectric substances that are inside here. So now we are not more dealing with a free space. So when you are dealing with a free space, that you have the epsilon naught, which is a constant value. But now that you are dealing with any other dielectric substance, it can be a paraffin wax, it can be wood or something, whatever that is being put inside the capacitor. So when you pick the real object, like the real capacitor, and you look at it, you see that the legs are not equal. And in between the legs, inside, that is where you can find these dielectric substances that I am talking about. So depending on whatever insulator material that they have used to make that capacitor. Then you can term that capacitor as that dielectric substance capacitor. So you see the permittivity here is also depend on the capacitance, or the capacitor also depends on the permittivity. So if you are not dealing with a constant space that has a constant value, so which means that depending on the materials, how the materials are when it comes to conduction, though they are all insulators, but some are there, they are more, they are very poor or very bad insulators than the others. And so we also have a bad insulator, it means that it can store more charges. And the reason is, if here is very thick, so there wouldn't be any influence between the positive and then the negative charge. So you are able to store plenty charges in both plates. And that will make your capacitance very large. So you can also calculate for the relative permittivity. So the relative permittivity will be the permittivity of the substance divided by the permittivity of the free space. So epsilon R, which is called the relative permittivity, will be the permittivity of the substance over the free space. So this is what we call relative permittivity. So take note, a question can be given to you, permittivity. Just a minute, just a minute. Hello.
Am I the only one experiencing the screen problem? It's not easy.
Now, if your screen is not showing, it means that your network, you check your connection. That's the reason. So it means that your internet is off and on.
Yes, I mean,
so
I'm in the typical place. It's not easy at all.
oh, sorry. Shall we walk?
Hello, sir.
Yes.
Please, I have a question.
Oh, you asked. Go ahead, please.
Okay. And what's the significance of relating the permittivity of the material to that of the free space?
Okay. No, the free space is just a value that is known, and that one is a constant thing. But the material is, it can be, just as I was mentioning, it can be any other material at all. So if you want to find the relative, so relative is a ratio. You are comparing something that is known to an unknown substance. So assuming in the question, you are not given the permittivity of that substance. You are only told that, oh, there is this substance which is being used as a dielectric substance, but their relative permittivity is this. And since the permittivity or the permittivity of the space is constant, then it can help you calculate for the permittivity of that particular dielectric substance. Then you can now use it to get the capacitance of whatever you are looking for. So it's just like a ratio, it's a standard. It's like you are measuring or comparing the speed of any other moving object to that of the speed of light. So that is the standard value that is known. So before you can measure any other thing, once you know the speed of light, if you know their ratios, then you can tell how much that particular object will be. So it's just like to help you compare the permittivity of the substance to the standard one.
Okay, so thank you.
You're welcome. Okay, so since we have this, we'll see the application. We'll talk about selecting it. Okay, now we pass there. Let's see if we can get a question on that. We solve move through. But you can also relate the capacitance to the electric field that we did the other time. So since you know that the field also has a relation with the charge, so you can also relate the capacitance and the charge together. So in the electric field formula, you can make charge the circuit. You can substitute it in the capacitance formula. Replace the charge with the expression you have in terms of field, so that you can also find out what happens if you have a bigger field. Will the capacitance increase or decrease? You can also do that. I'm searching for a question that so okay, so let's try this question and then see. So example, we have given that so one, given that the capacitance of a capacitor of plus 8 microfarad and the charge on the plate is the charge on the plate is plus 7 microcoulomb. Find the potential difference across the plate. Find the potential difference across the plate. So solution, we have our C to be equals to 8 microfarad. Then we have our Q to be equals to 7 microcoulomb. Then we are interested of finding V. So we know that the formula for finding capacitance is equals to the charge stored over the V, which means that our V equals to charge on C, which will give us 8 times 10 to the power minus 6 divided by 7 times 10 to the power minus 6. So minus 6 will cancel minus 10 to the power minus 6. Then we'll be left with 8 divided by 7, which means that our v will be equals to 1 point something. So 8, that's 1, 10. So that will be 1. Then 3, 30. 7 will go to
4.
yes.
1.14.
1 point what?
14.
1.14. Okay. And the unit is volt. Okay, so this is what you have. So let's look at another one. Let's look for another one. So example 2. So example 2 is also saying that find the capacitance of concentric spheres of radius 5 cm and 8 cm, given that. So find the capacitance of concentric spheres of radius 5 cm and 8 cm, given that epsilon naught is equals to 8.85 times 10 to the power minus 12 farad per meter. So this is what you're given. So solution here, the same way we will define our, let's see, we have the radius. So when you talk about concentric circle, so you have something like this, and you have another circle within. So from this to this one is, let's say, A, and from this to the other one is B. So the B is the longer one, which is the 8 centimeter. Then the A is the shorter one, which is the 5 centimeter. Now this gives you the difference in terms of the potential. Okay, so the V, you view the difference. So that's a D. So we will define our formula that we know the capacitance is equals to, we talk about epsilon naught A on D. Okay, so since this is a sphere, area of a sphere is equals to 4 pi r squared. Now the difference in D, that's the change in D, we have D will be equals to B minus A. That's the potential, the length, sorry. That's the length, the difference. So that will be 8 minus 5, and this will give us 3 centimeters, which is the same as 0.03 meters. So we are coming to substitute this to find C. So now we know epsilon naught to be 8.85. We know A to be 4 pi r squared, and we know D to be 0.03 meters. So we substitute here and simplify. So it means that our C will be equals to 8.85 times 10 to the power minus 12, 10 times 4 pi r squared, all divided by 0.03. Then simplify this, and whatever answer you get will be the equivalent capacitance. Yes.
In that case, the 4 pi r, the r square, what will be the value for r there?
Okay. That's the radius. So let me, I didn't even factor in that. The radius is given. Okay. So that's 5 centimeter, and then that. Okay, so let's see here. So use the B, because it's taken from the origin to B. So that would be the B. I didn't factor in that. The charges are going to be stored here. You have the charges storing at this point. So if this is positive Q, then you have negative Q being stored here. So this range is what we are having, the 0.3. Okay, but once the sphere is taken from the center to the outer of it, so use the B as your R. So change the B, which is 8, will be 0.08. So R will be equals to 0.08 meters. Okay. So here it's 0.08. So times 0.08 square. What's the answer we are getting?
Uh, 2.37 times 10 exponent negative 11.
2.37 times 10 to the power minus 11, right?
Yes.
So F. Okay, so let's do the last example and then move to the next thing. So the diagram, that's 3. The diagram below shows a network of capacitors. Connected to a 12-volt supply. Calculate the A. Calculate the A, effective capacitance. Then B, charge on the 4 microfarad capacitor. and then finally C, energy stored in energy stored in 1 micro F capacitor. And this is a diagram. So in the diagram, we have a capacitor connected to another capacitor that are connected in parallel. Then from here, they are connected to another capacitor. Then from here to a voltage. Okay, so this is a circuit. So we have okay. So this is our V. And this one was given as 20. So we have our 20 here. Now here we have our, oh, is it 120 or 20? This one should be 120. Then we have here to be 2 micro F. Then here is 4 micro F. Here is 1 micro F. And then here is 2 micro F. Okay, so now we had the diagram on the screen. We are going to answer the first part of the question. So this one, we are going to calculate the effective capacitance. Now, you have to be very careful when you are solving a problem like this. See that the capacitors, not all of them are in series, so that you can just go and use the formula that we saw, just taking the inverse of them and then sum them together. Some are in series, others are in parallel. So it means that you combine the two formulas that we saw. So first of all, if you look at it very carefully, it's like you have 2 circuits in one. So if you consider the smaller one, that where we have the 1 microfarad and then the 4, that one is a circuit of its own. And the capacitors there, the arrangement of the capacitors are parallel. Okay, so we need to find the equivalent capacitance there. Then use the equivalent capacitance in the smaller circuit with the bigger one to also find the capacitance there, and that will give us the total capacitance within the circuit. So if you take the smaller one, so solution, so A, so let's say I have taken the smaller one out. I'm going to have something like this. So let me add my voltage. So it's connected to the same power supply. So my voltage is going to be here. So let's say this is my voltage, the 120 here. So this time around, this is 1 mu F, and this is 4 mu F. Okay, so we established the relation that I'm not going to go through that. We know that if capacitors are connected in parallel, so we are going to sum them for parallel capacitors, parallel plate capacitors. The equivalent capacitance, that's the total, will be equal to the sum. So that will be C1 plus C2, right? So it means that our CT here will be equals to 1 plus 4, and it is micro. So that's times 10 to the power minus 6. So this will give us 5 micro F. So that is the total capacitance for the smaller one. Then I can now redraw this circuit. So I can redraw my circuit to be like this. So here is still my V, which is my 120 volt. And here from the diagram is 2 micro F. Now here will be the total that I've calculated for this smaller one. So that will now be 5. 5 micro F. And this one will still be my 2. So this one from the previous diagram that I sketched. So this one will still be your 2 micro F. So let's go back to this. So I've still maintained this one. I've still maintained my 2s, but this one is what I've calculated to be 5 here. So I'm also going to apply the law here for capacitor that are connected. So you can now see that all these 3, let me indicate this. So this is negative and this is positive, so that we know that this is a cell, not a capacitor. So all these 3 capacitors are connected in series. And once they are connected in series, so we have V1 here, we have V2 here, we have V3 here. So now we have the PD across this. And remember, the PD across these parallel capacitors is the same thing. So whatever PD you get for the 1 microfarad capacitor is the same thing for the 4 micro capacitor. So that's why we have a common PD there, just as V2. Okay, so we are still on A. We are still calculating for the equivalent. So we are now coming to take the inverse of these 3 and sum them. So for capacitors in a series connection, so for series connections, our total capacitance is equals to 1 over the sum of the individual. And so on. So 1 over CT will be equals to 1 on 2 plus 1 on 5 plus 1 on 2. I think that's what we have. 2 to 5, 2. So we have that. Then we'll find our LCM. Looking at this, our LCM is 10. Or you can even add the half together. So if you do that, this is going to give us 1 over CT to be equals to 1 plus 1 out of 5. So if you find the LCM, that will give us 1 on CT to be equals to 5 plus 1 all on 5. And this will give us 6 on 5. So which means that we have 1 over CT to be equals to 6 out of 5. But we are interested in making CT the subject, not 1 over CT. So we have to cross multiply. So by making CT the subject, taking the cross multiplication, and then divide through by 6. Yeah. Yes.
The LCM, the LCM, 10.
The LCM, oh, you can pick 10, you can pick 5. They said the least common factor. That's the LCM. So the least common factor here is 5. If you use a 10, you still get it right. So if you use a 10, it's still going to be the same thing. Because if we use 10, okay, let's see here, we're going to have 5 out of 6. Then F, so you can say it's 0 point something if you take to the decimals. So when you take the 10, so assuming you've taken 10 here, you are going to have 11. So that's 10. So you have 11 on 10. Then when you simplify this and mix it into this one, going to be 10 out of 11. So if you want divide 5 over 6 and also divide 10 over 11 and see, you get the same answers.
Yes, sir, it's true, sir. Thank you.
Okay. So we have 5 out of 6, or you can change it to the decimals if you have calculator. What is the decimal form?
0.83.
So this equals to 0.83F. So this will be our total capacitance. Okay. These are this will be the amount of charges that, yes.
So please, is it going to microfarad or only farad?
Oh, there's micro. There's micro. Because they are giving me. So you have to don't take it off. Yeah, so it's micro farad. Okay. So that answered the first or the A part of the question. Now the B is saying that, let me see, B. So if you understand, there's no need for you redrawing, but if you think if you do it this way, will make you understand better to solve it, you can. There's no harm in sketching again. You can do it and then solve for it. So the B part is that charge on the 4 micro F capacitor. So what is the charge that is stored in the, where is the original diagram? Yes. So we are now looking at the charges that are stored here. Here. How many charges will be stored in this particular capacitor? Okay. So let's look at what we've gone through already. We said when they are connected in, where is that? Yes. So this is for series connections. So the series connections, the charges are not same. So it means that each of them will have a charge stored, different charges stored. That is for series. But if you look at the parallel connection that we've gone through, parallel connections, where are you? So this is series, which we have. Yeah, so series connection, series connection, we have the charges being stored is equal, but the PD that varies. Then for parallel connections,
Voltage is the same.
so when it comes to parallel connections, the voltage is the same, but the charges that are also vary. So you come and use your formula. So you come and use your formula here. So B you have the capacitance should be equals to the charge over the V. So that is what you will state. Now, since we know that the potential across the parallel connections is same, so if we know how much PD that is going through this 5 microcoulomb, a microfarad capacitor, then we can use it to calculate for the 4. So what we need to do is that we need to calculate for V2. If you get V2, then we'll use V2 to get the charges that are stored in the 4, because you can't pick the 120 straight. When you pick the 120, it means that everything that's stored is only this charge that absorbs this PD, but there are a lot of capacitors, so you have to calculate for each of them the potential for each. Then you pick the V2 to now calculate for the charges stored in 4. Okay, so let's do that. Now we have the total capacitance. So if we have the total capacitance, then we can get the charges here for the second diagram that I've sketched. So here, because the charge is going to be constant throughout, for here the charge is going to be constant throughout. So you can calculate for V1, V2, and V3. So from the diagram, the other diagram, so we have CT to be equals to KO over V1. That's for this diagram. I'm using this one, this diagram to do it. Yes.
Yes, sir.
Mhm.
Please, can we say the charges that are going to pass through the 4 microfarad and then the 1 microfarad capacitors will be the same?
Yes.
So if it will be the same, then
Now the
is it
charges will
going-
not be the same thing. It's the PD that will be the same.
Yes. So the charge is going to split for them.
Yeah, it was split. The charge was split.
I'm asking the 120 volts.
Will be
Oh,
same.
okay. Will be the same.
So let's say this is the joint. So let's say that the charge is coming from here. Once it
Yes,
gets to this joint, some will be going up here and others will be going down there.
Yeah, so I want to know if it's going to divide equally so that we will say 60 is passing here, 60 is passing through.
No, it will not be equally because of their sizes. Their sizes are not same. Remember, I said the area depends on what? The capacitance depends on the area. So if the area is big, you have more charges being stored. So you have 1 and then 4. There's no way that the PD across them or the charges that are going to, no, the PD across them are going to be divided equally, but it rather be the same thing. So the 120 will be the same thing. So let's say you have something that is like this. You have a current that is coming in here, and you have this capacitor, you have this one too, and this is joining this. So this is where your V is. Okay, so if you bring a voltage to measure the PD across this, you just put your V here, and then it will be recording whatever that is going through here. So you see that the potential difference is common for the two, but the charges is like in a form of current. So if you have a current that is flowing, so this is I that is coming from this direction. So when you get here, it will split into two. So you have one, that's a I1 going here, and you have I2 that will also be going here. You understand? So the same way the charges. So the charges that will be stored here will not be the same as the charges that will be stored here. So you need to calculate the individual charges by using this scenario that the voltage is common for the two. Okay, so
okay, sir.
So
Sir,
CT,
please.
okay.
So
Yeah,
please,
come.
if the voltage is going to be common, so then why can't we just go straight forward and multiply the 4 microfarad by the 120 volts so that we can get the charge that will be stored on that capacitor?
Yes, but it's not 120 that is coming to this one alone. You know that there are others. Don't forget about our original diagram. You see that the PD that is going through here, these two will not be the same thing as whatever that is going through the combination of these two. So when we force these two to combine, like the way we have it here, like here. So you see that we have different V's. We have V1, V2, V3, which means that whatever V1 that will go through 2 microfarad wouldn't be the same thing that is going to the 5. So you can't use the 120 like that. So you have to see how much will the 2 will take. So if 2 is taking like 10, then this 2 will also take 10. So the remaining will now go through the 5. I don't know whether you're following what we are saying.
Yeah, yes, I'm following.
So you can't just pick the 120. So when you pick the 120, that it means that you are assuming that these two capacitors are not there. It means that V1 will not be there, V3 will not be there. So you are only left with this 5. So that's why you can pick the 120. But because there are some other capacitors, you need to calculate for the PD across each of them since they are in series connection. So when you get V2, instead of V2, you now use V2 to get the charges that are stored in the 4. Can we proceed from there?
Yeah.
Okay.
Yes, ma'am.
So now that we have this formula, so you are using the figure. So our total, now we know that this is the equivalent capacitance. That's the total capacitance there. So when you pick the individual one, so let me go with this so that we understand. So let's say pick this. So you have C1 to be equals to charge over this. Now we want to calculate for V1. So this implies that our V1 will be equals to Q on C1. Okay, so let's come back to this diagram. This one. Now, what is our V1, our C1? C1 is 2, right? And then the charge here, the charge is constant because this is a series connection. So our charge is going to be Q. So let's find the total charge first. Let's find the total charge first. So let's find the total charge before we now come to the individual charges. If not, we don't have the charge. So we are saying that the C total is equals to this. So in that case, our charge, the total charge will now be equals to the equivalent capacitance times the voltage. And our total charge will now be equals to, we have it to be 0 point something, 0 0.83, 0 0.83 times 10 to the power minus 6, now times 120. So let's get this answer. What are we going to get?
So 9.96 times 10 exponent negative 5.
9.96 times 10 to the power minus 5, right?
Yes.
Column. So which is the same thing as if you move to this, so that will be 99. So 99.5 micro column. So you have this. So it means that this is a total charge that will be going through this circuit. And since they are in series connection, it means that the charge is going to be common for all of them. So it's the same charge that will go through the 2 microfarad charge column capacitor, the same charge that will go through the 5, and the same charge that will go through the 2 here. Okay, so now that we know the charge, we can now calculate for the individual voltage across each of them. So by using this formula, so we have our C1 to now be equals to the total charge over V1. So this implies that our V1 will be equals to the total charge that we have divided by C1. So which means this will be equals to 9.96 exponent 5 times 10 to the power minus 5. Now divided by, we are dealing with 2. 2 times 10 to the power minus 6. So compute this one. And let's see what we're going to have. Yeah, what are we getting for V1?
It will be 4.98 times 10 exponent negative 11.
4.98. No, it cannot be negative 11 because already this is negative. When it goes up, it becomes positive. Then you have minus 5 plus 6. Check your
Yeah.
calculation. It's not right. You should be getting like 54 something. Because 9.96 divided by 2.
So it is 49.8.
Okay. 49.8.
0.8.
So 49.8. And this one will give us volt. So the same value that we'll get for this one, the other two. So it's the same thing. The V3 will also be the same thing. So it means that you can say that V1 is equals to V3 is equals to V3. V3, which is the same thing as what? 49. You said 0.8,
Yes.
0.8 volt. So this is what you have for the two. Now, if you want to get the last one, you can calculate, or you add these two and subtract from the total. So let's say for the V2, V2 will be equals to, we also have the total charge divided by C2. And that will give us total charge is 9.96 times 10 to the power minus 5 divided by 5 times 10 to the power minus 6. Then what answer we get?
$19.92.
So it means that our V2 is equals to 19.92
Yes.
volt. So it means that for this capacitor, the sum of these two capacitors, it allows only 19.9 something to go through it. So per what we said, no, if you want to check whether you are true, you are right or not, but we said for parallel series connections, the PD is equal to the sum of the individuals, so V1 plus V2 plus V3. So when you sum these three, we should get the 120. So let's say this will give us, we are saying that V1 is the same as V2, so it means that we have 2 times 49.8, because we have 49.8 plus 49.8, so I've just multiplied by 2, then plus 19.92. Add them together and let's see whether we get 120.
Yes, approximately 119.52.
Okay, so you see that we are getting approximately the entire or the supply voltage that was given. So when you do it and you are not getting the same thing, it means that your calculation is wrong. Okay, so now we have our individual potential differences across each capacitor. We can now go and then answer our B. So we are almost done. So the B is now talking about the 4 microfarad capacitor. And we know that the voltage is common for all of them. So once the voltage is common, then we use the 19.92 to get the charges that are stored there. Do you understand?
Yes, sir.
Yes, sir.
Okay. So to get the charges there, you will now have, so C is equals to charge on V. So that's for the 4 microfarad capacitor. So since the voltage is common, the voltage is 19.92, and the capacitor is 4. We are interested in charges, so we have our charge that are stored in the 4 to be equals to CV, and the capacitor is given as 4, then times 19.92. So whatever answer you get will be the charges stored in that.
So please, it's 4 microfarad.
4 micro. So 4 times, so that will be 4 times 10 to the power minus 6 times 19.92. What are we getting?
79.68
79.68
yeah,
So-
microcoulomb.
times 10 to the power 6.
Yes.
Okay, so micro. So this would be the charges stored in that particular capacitor. So this can be a full question in session B. Then the third part talks about the potential energy stored. So the energy is stored as a potential energy. So when we were talking about the electricity, we said the potential energy is the energy or of a point is what the work done in bringing a unit charge from infinity to that point. So you can also define our energy stored in terms of what?
Okay. Somebody background is disturbing.
Please kindly unmute yourself. Thank you. So we define our potential energy as U to be equals to half K square on C. So the charges square divided by the capacitor, and then we take half of it. Okay. So the question is saying, are we calculating the energy stored in 1F? We are not calculating for the entire energy that is stored. If we're to be the entire energy stored, we have to get the individual charges stored in each capacitor. Then we sum them together to get the total charges that will be stored in the circuit. Then we'll now square it, divided by the capacitance, the equivalent or the total capacitance within it. Then we divide it by 2. That's what we should have done if we were calculating for the total energy that will be stored. But we are only interested in the energy that will be stored in only the 1 microfarad. So you use this formula. So we need to get the charges that the 1 microfarad will store. So the same way as we calculated for the 4 microfarad, we'll still use the same voltage because it's the same voltage that will also go through for the parallel connections here, where I sketch the individual one. So here, the first one here. So here the PD is the same thing here for these two, but we are interested, so we still use the 19. So we use the 19 to calculate for the charges that are stored here and use that one with the capacitor value to get the energy. So for the 1 microfarad, so we'll have, okay, this one should be C, not B. So C, so we need to get the charges stored in the 1 microfarad capacitor. So in that case, we'll have our C to be equals to the K on V, on the V. Now, so K will be equals to 1 times 10 to the power minus 6 times 19.92. So let's get this. So the charge is stored in the 1, in the 1 microfarad capacitor is giving us. So what are we getting?
19.92 times 10 to the power minus 6.
19.92 microcoulomb. So this will be the charge. So for the potential energy stored in 1F microfarad capacitor is, so you now have your potential energy U to be equals to half K square on the C. So in that case, we're going to have 1 on 2 times the charge that will be stored there is 19.92 times 10 to the power minus 6 squared, then divided by, we have the charge, which is 1 times 10 to the power minus 6. So simplify. So in that case, you have this to be equals to 19.92 squared times 1 times 10 to the power minus 6. Because times 10 to the power minus 6, 1 is here, we cancel one of it. So this one would be square, but this one will take away, or you just compute everything direct, divided by 2. And let's get the potential energy.
198.
198.4
times 10 to the power minus 6.
198. 0.4 times 10 to the power minus 6, right?
Times.
So joules. So that would be the potential energy stored in this particular capacitor. Okay. Any question, please? Any question? Do we understand?
Yes, sir.
Okay. I hope when you get a question like this, you should be able to solve it.
Hello, sir.
Yeah.
Hello, sir.
Yes, I'm with you, please.
Sir, can we have the slide when you're done?
I will send it to you.
Okay, please. Thanks.
When I'm done, I will send it to you. Okay. So can we move on? Let's close at 8:30 so that we know that we are done with 2 hours. We will meet for another 2 hours. So the next thing we'll be looking at is I think we have, when I explain this, we'll move to the last unit where we'll be talking about current, electricity, and those things. So that will be our next meeting when we are meeting. Yeah, because you know where we are going to examine you on. Okay, so we will talk about magnetism. That's the next thing we will talk on. So since the cause is electricity and then magnetism, so they go hand in hand. So we are not done talking about the electric part of the cause, but we have to say something on the magnetism part as well, because they go hand in hand. You can induce an electric field when you have a magnet or a magnetic substance. The same way you can also obtain an electric field from a magnetic substance. So a magnet, as we know, is normally a solid bar that has different magnetic properties. So though it is just a single one, but it has different magnetic properties in them. We always have the magnetic lines moving from the North Pole to the South Pole. So just as we discuss the electric charges, we have positive terminal and then we have a negative terminal. The same way, when it comes to the magnetism, we also have the North Pole and the South Pole, which is also talking about the polarities of the bar. Now, this magnet that we've been talking about naturally was obtained from a lost stone. Okay, so it's just like an iron oxide. Okay, so the magnet is obtained from an iron oxide, and it has magnetic properties. So when you pick a magnet, you will look at the poles, and the poles are the south and then the north. But even that, we have different type of magnets. We have what we call the ferromagnetic substance or materials, and we also have the non-magnetic substance. Now, the ferromagnetic substances are those magnets that do not lose their magnetic properties easily. Okay, they are very strong when it comes to attraction of objects. So for them, they don't easily get loss of their magnetic properties. But the non-magnetic substances are those that can easily be demagnetized. Okay, and they are mostly not attracted by some materials. Okay, so they are the magnetic and those that cannot attract. That doesn't mean that they don't have magnetic properties in them. They have, but it's very weak. So once it is weak, they cannot attract. So for instance, when you talk about the non-magnetic substances, you can talk about the brass, the wood, copper, and then glass. All these are not attracted by a magnet. So you can call them non-magnetic substances. But the one that get attracted by the magnet are what we call the magnetic substances. Okay, so as I talk about the north and then south pole, when you take the magnet, then these poles are aligned. They usually move from the north to the south. That is how the magnetic lines are. And yeah, so the lines, we saw the flux the other time that we met. So when you talk about the amount of field lines that are coming out from a magnetic substance constitute the flux density. So you have the lines, then we talked about them that they never cross each other. We have the neutral point, that is if we bring two polarities of a magnet together, you have the lines never touching each other. Yeah, I think we've gone through this one the last time, so I will just even skip it. We did this one the last time that we met. Okay, so I think the magnetism of like that what we did the other time, we covered everything here. The only thing we didn't talk about is the right hand rule and then those things. So I think that was the only one that we could not mention. Yeah, because the other time I didn't use your model to teach. I used a different book which captured everything here because I was following your model. So we did everything here. Everything under magnetism. We go to this next session. Charge particles in a uniform magnetic field. Magnetic force and current conductor. Okay. So go through this. Okay. So I think what we need to do here is only the unit 2 session 3. Unit 2 session 3. I think that's the only thing, but the 1 and 2 was what we did the previous week, before last week, previous 2 weeks. Okay, so you let us pause here. When we meet, maybe tomorrow is a holiday. I don't know how busy you people will be. So since it's a holiday, we'll not worry ourselves like that. But maybe Tuesday, we don't have a class in the evening. We can meet. And Saturday class will come off. Because, yes.
So out of Monday, because Tuesday is like we have class.
Okay. If you are free on Monday, that's fine. We can also meet on Monday.
Monday will be holiday, so if that's my
so
suggestion. But my colleagues, I don't know where they'll see.
That because I don't know your schedule, that's why Monday to not all that.
And Monday is holiday, but Tuesday is not holiday, but Monday is holiday, I guess.
Okay. So we meet on Monday, right? For the 2 hours that's left. But Saturday, if nothing happens, we can still meet for our normal lectures that we are supposed to have. So meet on Saturday and then God willing Sunday. But next week will be articles. Okay. So any question or any other suggestion? Hello, any question? Any other thing that?
The only problem some about we couldn't join the previous lesson. The other one.
I've sent you the
network.
I've sent you the slides. Everything is on the platform. You see, the second one, we wanted to stream it like YouTube. So it was online, but because it was the first time, we were having some challenges with the system. So I think that is why, see, we'll be having the lecture, it gets to a point and we have to pause and then do some settings before we come back. Yes, that's Steven.
Hello, sir. Sir, please, the slide, who do you contact for the slides?
Oh, I've sent it to the platform, the physics major discussion.
Okay, I'm not there, that's why. Okay.
Oh, then let them add you.
Okay, sir.
So all of them are there.
Frank, please kindly add me, Frank.
Yes, I'm not the admin.
So
Let me
give
see.
my number to administrator. I don't so that you can add me. Who's the administrator?
Let me check. Physics major discussion. I'm sure I will be one of the administrators. Mm, yeah, so you try joining, it'll come, so that I'll just tag and then you. Okay, once you set you are not then I'll forward the link to you, okay? But I don't also have your number. How do I do that?
So please, if you can give me your number so that I can give you a hello.
So use 0240.
Okay.
That's two numbers. So 0240 87
87
85
85.
84. Okay, who is here? Let me make the person one of you there, I mean, so that anybody that is not there, you can just add the person. Mention your name and let me see if you are in the platform so I can make you the administrator. If you are here and then you are in the platform. Stephen, you are here, okay. Stephen. So let me search you. I'll make you the admin so that you can add. You can add anybody that is not there. That's your WhatsApp handle, or you use your name. You use your name, please, or you use a different. I'm sure.
Hello, sir.
Yeah.
Yes, sir. Please search Frankies. You see FRANKEYZ.
FR
ANKEYZ.
FR
ANKEYZ.
Frank.
Yes.
Mm-hmm.
EYZ.
EYZ. I can't see you.
Oh,
I only saw cafe. I've seen you.
okay, sir.
I've seen that you've tested something. Okay. I've done that. Okay, so you can add any other person that is not.
Okay, sir.
So I've added you. I've made you the administrator. Okay, so we'll end here, please. God willing, we'll meet on Saturday.
When I Ndawe kama kwa. Kama dada wasa dada man. Mimi kula. Mimi baba na zai mai ka bi shi wani. Na zamin da alun na yakan. Kin ne gaba da wani su. Allah an ba kula. Azula mai ran. Mai ne kuma. Da abban nan ba kuntuwa mu sai karbara. Tam da hana ba ma nyira man tu a de hoya. Yana manya.
I don't know abuma za na ba take for nothing like that even. Only another you got the but others. Abuma za.
Bi yodo ga an kawai.
Kabat yes. Ina ngaban tekcha.
Yodo ga.
Kaban irana ba ta fanci da maka banne ka tu goma gona ban ta wuya.
Bi ya daughter men content one. Ban content one.
Chama na ne ka ri goma man na.
You work.
Nayan akubala ina ko ce abuma ba je ko na da tin da tamba an da ruwa na. Jabatin ka da ya da ina da biyo sai kan ga ko ne ku biyo no ku ci ina na kan.
Babu. Abiye bangali.
Ni ka jin da.
Kana je ko fara ba na de moto ga.
Na bando sai kan ga ta ji wo ne biyo ni ne ko je.
Ni go ga wo.
Now we are going to challenge. Which will be a young bad. Say for a little one, you can't hide. Yeah, but you see a young will allow what I would say.
Manzana. Framework. 2021 kasi 2011. Oh, so time is losing. Me and my husband Meleo. It is. Women am what I'm going to kill you. I didn't kill my Bonka TV ngambala tuno bwayo. Wala ka decoder ngaba. Ye change mo be na ka ngala tu. Be mo pa tu pa ka dek pa ma wa.
Open the bedroom not to know.
Bo mo yen pan change ruke.
I'm on the chat with you.
Unlawfully disclosing or altering a deal comes also with some heavy sanctions. There are cases that are going to court.
Charlie, stop to ABC game, but what's up? I am ready to say ABC.
One day.
Ariana.
Maybe what you get my son, the kind of Where you are from? Line 3. Bien, y ella con la base.
Mama. Red pencil eyeliner. Red pencil eyeliner. Red pencil eyeliner. Bring the book and write. Can you write? Write one. Two. Two. Don't write two. Two. Yeah, right. Two. Right. If you don't write, I will not buy soda. Oh, that's not. Something Monday. Something Monday.
What are you? Wanyama. So what's in Zoom and Hey, my God. Hey, apa nak curu dah?
Oh.
Maybe I find where you were standing. Hey, Austin, quite a book anyway. What's it? Wait a minute, funny video. It's good to whatever. Oh, kalau naik kawasan mana membuat plan le. Dia apa? Dia.
What's the idea? Ah.
Nama kau yoga apa sih? Pasti yang dia mahal. Barang macam Bati. Pagi. Serah. Nembak pun. Thank you. Aku minum.
Hey, itu apa maksudnya? It's finished.
Ni to ba mi bile. Mo ni mi bile ma de ho an tre to.
I'm not able to do that much to catch. Finish. What I find here for the one. So you finish writing it.
What na bum ya da mun to para ka. Ya ba to ba. Number 5.